Good morning, student. Today, I would like to discuss one of the important correlation analysis that is called Taft equation. In my earlier lectures, I had already discussed with you about the most important linear free energy relationship that is called Hammett equation. You all are aware of this very important Hammett equations, but there are few limitations. Actually, Hammett equation is only applicable for para and meta substituents compound. And second problem of the Hammett equation, that it is only applicable for aromatic compounds. Like we have already seen that the pK of different substituted benzoic acid, we have already seen that alkaline hydrolysis of ethyl benzoate and different substituted ethyl benzoate. And there are certain other non-linear Hammett plots. Today I will not discuss about the limitation of the Hammett equation, but it is a very short lecture, and today I will only give you an introduction to the Taft equation, that what is the basic idea of the Taft equation and what is the final form of the Taft equation, and what is the difference between the Hammett equation, which is an example of simple linear regression analysis, whereas Taft equation is multiple regression analysis. So I will explain that some of the basic concepts of that Taft equation. Now, before I start the Taft equation, you must know that when it was discovered. So it is a very old equation, and a great scientist, Professor Robert Taft, he actually in 1952 he published a couple of papers, and his first paper is published in, you have seen, American Chemical Society Journal, and that was linear free energy relationship from the rates of esterification of hydrolysis of aliphatic and ortho substituted benzoate ester. It indicates that Taft equation is applicable for ortho substituent compounds of the benzoate ester, as well as some Taft parameter is also there, and he has taken some of the aliphatic compounds. And this is the actually original research paper, you see, and after that he also published another paper, because whenever you are talking about the Hammett equation, you know that I have discussed that three different effects. One is called the polar effects, another is called the resonance effect, and steric effect. So it is very important that how do you identify or the separation of polar, steric and resonance effect. And if you see this paper, actually this paper gives a elementary idea about the separation of this polar and steric effect. For that he has taken acidic hydrolysis of aliphatic ester as well as the basic hydrolysis of the aliphatic ester, and then on the basis of this result he actually distinguishes between the polar effect as well as the steric effect. I will come to that point. And fortunately there are a large number of very good books available in our library. So in order to understand the complete, because it is not a very small effect, there are many applications of this Taft equation. So one of the best book is Physical Organic Chemistry by L.P. Hammett. So you can call it the extension of the Hammett equation. So you can get complete information of that Taft equation. Another book is very important. You know that Hammett equation by C.D. Johnson. This book is also available in our library, and as because these are all linear free energy relationship, or sometimes we call this a correlation analysis. So there is a book by John Shorter, the correlation analysis organic reactivity, with particular reference to multiple regressions. There are, after the Hammett equation, there appear large number of other equations also. But today I will concentrate only on this, that Taft parameters, and very as far as it is in actually M.Sc final year course in physical organic chemistry. So I will give only very elementary idea about this. Today I will not discuss about the ortho effect or the application of the Taft equation. Now this is the, actually you all know that we must know this great L.P. Hammett, who actually discovered this most important equation. As you know that log of K and K0, it is substituted compound and is a reference compound when substitution is hydrogen, and you know that this is the most important parameters, sigma and rho, and which is called the substituents parameters, and it is a sensitivity constant. This is actually Hammett equation, and this is actually Taft. And as I have already discussed with you, that some of the important paper of the R.W. Taft, it is a quantitative structure reactivity relationship, and it is applicable, useful for the aliphatic compounds and of course the ortho substituents compounds. And of course he actually modified that Hammett equation. I have taken this photograph from the Wikipedia. Now most important point is that how do you separate the polar, steric and resonance effects? And actually the Hammett equation accounts how field effect, inductive effect and resonance effects influence the reaction rates, whereas Taft categorically, if you understand the Taft equation, you are able to identify the steric effect as well as the polar effects. I am coming to that point, that how do you understand the steric effect and the polar effect, by giving a very simple example of acidic hydrolysis of a aliphatic esters. Now why another important point is that, as I told you, that the Hammett equation is, that means if we plot a graph between this and substituent parameters, so there will be a straight line, and with the help of slope value we can determine the sensitivity parameters, or sometimes it is called the reaction constant, and with the help of that reaction constant we can predict or we can figure out the reaction mechanism. Whereas in Taft equation, that is always called dual substituent parameter equation. That means there are two important problems, like that if you all know that y is equal to mx plus c, just simple straight line equation. So only one parameter is there. So the simple linear regression analysis can be sufficient to study this. But suppose there is more than one parameter, like if I write it is m1 and x1 plus m2, then x2, like and plus c, like that. So there are two parameters. So therefore it is called dual substituent parameters. It is one of the most important example of multiple linear regression analysis, and it accounts two parameters. One is, as you know, polar parameters. In order to distinction between that aromatic compounds and aliphatic compounds, here it is like that, this type. And second is that steric parameters. So that is the difference between the Hammett equation as well as the Taft equation. Now, if you ask me, sir, what is the final equation of the Hammett equation, the Taft equation? So same, just like your Hammett equation, just I always write so that you can very easily understand. This is K0 and this is substituents. Like that. So same equation you see, but here is also, this is the substituted aliphatic compound. I will give you, suppose if I write like that, X CH2 CO R1 like that, suppose. And here for Taft equation, in Hammett equation, suppose if I were taking the benzoic acid is the unsubstituted compound, and then so ethyl benzoate, substituted ethyl benzoate. So here X means CH3, that means this is the ideal compound. So this, therefore I have written here KCH3, where the value is 0 like that. So this is actually, here X is equal to hydrogen, so CH3. And then of course you substitute with some aliphatic substituents. So, and Kx is the substituent compounds, and this is the reference. So you see that two parameters. One parameter is polar parameters. I will discuss these things. And second parameter is this steric parameters. So if I combine these two things, actually he studied separately acidic hydrolysis first, and then he also studied the base hydrolysis, and then monitor steric effect and polar effect separately, and then he combined these two equations. So we'll get the final equation, and you know, this is sensitivity parameters is also there, this is also sensitivity parameters is also there. So here, as I have already told you, that this is sensitivity factors for the reactions, for the it accounts the polar effects, whereas this delta, that part, that accounts the other effects. And then of course sensitivity parameters that account the steric effect. So by that method he determined the different values of these two constant, that polar constant and steric. I am giving some of the values here, and these parameters are available any standard physical or organic chemistry book, and I am showing of some of the parameters. As I told you that this is our reference compound where it is CH3, so you know his value is 0, whereas in Hammett equation we call it is a parent compound is H is equal to 0, and then if you want to substitute it ethyl or propyl or butyl like that, so we are getting different types of polar constant and the steric constant. And if you know the values of steric constant and polar constant, and of course the rate constant, then you can plot a graph between that log K and so then that the nature of the graph may be like this type of the thing, maybe this type of graph observed. So on the basis of this graph you can identify the types of the reaction mechanism, you can predict some light on this mechanism. Similarly, and again it is multiple linear regression analysis. So this is for aliphatic type of the compound. As I have already discussed with you that this Taft equation is also applicable for ortho substituents aromatic compounds. I am also showing some of the values of ortho substituent benzoate. Here is also same thing, or parent compound is this, and then of course because here it is ortho substitution, not para or meta substitution, which is the Hammett equation. But here I am talking about the Taft equation, T-A-F-T, Taft. So therefore, you see here nitro, nichloro, bromo, the values of ortho substituents, polar constant, ortho substituents, steric constants, the values. I am giving only one or two values, and most of the values are available in any standard textbook of physical organic chemistry. Now let me explain the genesis of that Taft ticket, because they have chosen two things. One is for acidic hydrolysis of the carboxylic ester, another is the basic hydrolysis. And on the basis of these two simple parameters, or you can call it R1. So you know that there are two steps. One is first, if it is acid hydrolysis, so naturally, if it is, so first is the protonation step, and second is the nucleophilic attack of the water. I am talking about that. First is that acidic hydrolysis. So I can write like that, R, C. So it is a protonation part is there, and then OR1. And here, you know, this is a transition state of acidic hydrolysis plus. Okay, this is for acidic. Similarly, for basic hydrolysis, you know the proton abstraction. So here the structure is slightly different, and you know it is RCO OH. Its formula is RCOH. I'm sorry, this must be OH, because protonation is here, only O is there. Because this is protonation step. So total, now if you just compare these two things, that means log of K X K methyl for acidic, and again log of Kx K methyl for basic, of course. And if you see very carefully why it is the basic hydrolysis and acid hydrolysis is accounts for, here is steric effect, and that accounts for the polar and resonance and steric effect. If I minus subtract, then of course the actual polar effect can be emerged. How? Because if you see here the transition state 2 and 1, 3 proton, and here is only 1. So which is bulky, this is 2 hydrogen is extra. So on the basis of these two experiments, R.W. Taft determined that a very common equation. Of course, the equation is like that, same thing. Kn or Kx and Kch3. This, if I write like that, so you see that this is for basic and this is for acidic, and this is actually value. That means if I write like that, log K by K0 sigma rho, and the rho value is 2.48. Here is again, if I write CH3, also CH3. So it is polar substituent constant, as I have already told you. This is substituted and K0 is CH3. So this equation is actually accounts the difference between the steric effect and polar effect, and for acidic hydrolysis it measures the steric effect, whereas in basic hydrolysis measure the polar effect, and the same equation can be used for the substituted benzoate esters. So this is another example of Taft equation where that for it can be used for aromatic compound. Condition is that ortho substituted aromatic compounds, like that. You know, very simply equation I have written here. So it is ortho substituted, but the condition is that here the reference means that is methyl, and then you can go on substitute the nitro, chloro, bromo, methoxy, and different types of the compounds. And finally, I have already told you that according to the Taft, the electronic factors of the substituents have little effect on acidic hydrolysis of aliphatic esters. Therefore, this log Kx and K0 measures the sum of steric and resonance effect. And for acidic case, 2 hydrogen is there. So log Kx and K0 means you can call it as CH3. It gives the steric contribution, whereas for basic it gives the steric resonance effect. So ultimately what we are getting that for basic hydrolysis it gives polar, steric and resonance effect. So if I subtract from basic to acid, so we will get the actual polar effect, because for basic it gives polar, steric and resonance. For acidic it is only for steric. So if I subtract, so it will get the actual polar effect. So therefore we are getting the polar substituent constant. So as I have already written here. This is the beauty of the Taft equation. And what are the final outcome of that system? That the change in free energy of activation, delta G. Whatever the change in free energy of the activation, it is treated as the sum of, it is actually sum, ACM, sum of composite value, independent contribution of the polar, whatever you are getting the free energy value, it is due to the independent contribution of the polar, steric and resonance effect. But in Hammett equation you can't explain that steric effect and other things. And of course for acidic and basic hydrolysis the resonance and steric effects are same. Only thing is that for basic hydrolysis the polar effect of substituents in basic hydrolysis is greater than the acidic hydrolysis. That is the conclusion. Now the last part is that if you want to apply